In statistics, the Earth mover's distance, EMD, is a measure of the distance between two probability distributions over a region D. In mathematics, this is known as the Wasserstein metric. Informally, if the distributions are interpreted as two different ways of piling up a certain amount of dirt over the region D, the EMD is the minimum cost of turning one pile into the other, where the cost is assumed to be amount of dirt moved times the distance by which it is moved. The above definition is valid only if the two distributions have the same integral. Informally, if the two piles have the same amount of dirt, as in normalized histograms or probability density functions. In that case, the EMD is equivalent to the first Mallows distance or first Wasserstein distance between the two distributions. Theory. Assume that we have a set of points in R, D, text style, mathbar, R, D, dimension, D, text style D. Instead of assigning one distribution to the set of points, we can cluster them and represent the point set in terms of the clusters. Thus, each cluster is a single point in R, D, text style, mathbar, R, D, and the weight of the cluster is decided by the fraction of the distribution present in that cluster. This representation of a distribution by a set of clusters is called the signature. Two signatures can have different sizes. For example, a bimodal distribution has shorter signature, two clusters, than complex ones. One cluster representation, mean a mode in R, D, text style, mathbar, R, D, can be thought of as a single feature in a signature. The distance between each of the features is called as ground distance. The EMD problem can be solved as a transportation problem. Suppose that several suppliers, each with a given amount of goods, are required to supply several consumers, each with a given limited capacity. For each supplier-consumer pair, the cost of transporting a single unit of goods is given. The transportation problem is then to find a least expensive flow of goods from the suppliers to the consumers that satisfies the consumer's demand. Similarly, here the problem is transforming one signature, P, text style P, to another, Q, text style Q, with minimum work done. Assume that signature, P, text style P, has, M, text style M, clusters with, P, equals, opening curly bracket, P1, W, P1, P2, W, P2, P, M, W, P, M, closing curly bracket, text style P equals, P underscore 1, W underscore P1, P underscore 2, W underscore P2, P underscore M, W underscore PM, backslash closing curly bracket, where P, I, text style P underscore I, is the cluster representative and W, P, I, text style W underscore pi, is the weight of the cluster. Similarly, another signature, Q, equals, opening curly bracket, Q1, W, Q1, Q2, W, Q2, Qn, W, Qn, closing curly bracket, text style Q equals, Q underscore 1, W underscore Q1, Q underscore 2, W underscore Q2, Q underscore N, W underscore Qn, backslash closing curly bracket, has, N, text style N, clusters, let, D, equals, D, I, J, text style D equals, D underscore I, J, closing curly bracket, be the ground distance between clusters, P, I, text style P underscore I, and Q, J, text style Q underscore J. We want to find a flow F equals F I J. Text style F equals F underscore I J. Closing curly bracket with F I J. Text style F underscore I J. The flow between P I text style P underscore I and Q J text style Q underscore J that minimizes the overall cost. Min I equals 1 M J equals 1 N F I J D I J. Display style min sum underscore I equals 1 caret M sum underscore J equals 1 caret N F underscore I J D underscore I J. Subjected to the constraints F I J 0 1 I M 1 J N. Display style F underscore I J GEQ01 LEQI LEQM 1 LEQJ LEQN J equals 1 N F I J W P I 1 I M. Display style sum underscore J equals 1 caret N F underscore I J LEQW underscore pi 1 LEQI LEQM I equals 1 M F I J W Q J 1 J N. Display style sum underscore I equals 1 caret M F underscore I J LEQW underscore QJ 1 LEQJ LEQN I equals 1 M J equals 1 N F I J equals min I equals 1 M W P I J equals 1 N W Q J. Display style sum underscore I equals 1 caret M sum underscore J equals 1 caret N F underscore I J equals min BIGL sum underscore I equals 1 caret M W underscore pi sum underscore J equals 1 caret N W underscore QJ big R. Closing curly bracket. The optimal flow F text style F is found by solving this linear optimization problem. The Earth mover's distance is defined as the work normalized by the total flow E M D P Q equals I equals 1 M J equals 1 N F I J D I J I equals 1 M J equals 1 N F I J. Display style EMD P Q equals frac sum underscore I equals 1 caret M sum underscore J equals 1 caret N F underscore I J D underscore I J sum underscore I equals 1 caret M sum underscore J equals 1 caret N F underscore I J. Extensions. Some applications may require the comparison of distributions with different total masses. One approach is to allow for a partial match, where dirt from the most massive distribution is rearranged to make the least massive, and any leftover dirt is discarded at no cost. Under this approach, the EMD is no longer a true distance between distributions. Another approach is to allow for mass to be created or destroyed on a global and or local level, as an alternative to transportation, but with a cost penalty. In that case, one must specify a real parameter sigma, the ratio between the cost of creating or destroying 1 unit of dirt and the cost of transporting it by a unit distance. This is equivalent to minimizing the sum of the earth-moving cost plus sigma times the L1 distance between the rearranged pile and the second distribution. Notationally, if pi p q display style pi p to q is a partial function which is a bijection on subsets p single quote p display style p subset p and q single quote q display style q subset q, then one is interested in the distance function pipe p minus q pipe pi equals pipe p p single quote pipe plus pipe q q single quote pipe display style pq underscore pi equals p set minus p plus q set minus q, where p single quote display style p set minus p denotes set minus. Here p single quote display style p would be the portion of the earth that was moved. Thus p single quote display style p set minus p would be the portion not moved, and pipe p single quote pipe display style p set minus p the size of the pile not moved. By symmetry, one contemplates q single quote q display style q subset q as the pile at the destination that got there from p, as compared to the total q that we want to have there. Formally, this distance indicates how much an injective correspondence differs from an isomorphism. Computing the EMD. If the domain D is discrete, the EMD can be computed by solving an instance transportation problem, which can be solved by the so-called Hungarian algorithm. In particular, if D is a one-dimensional array of bins, the EMD can be efficiently computed by scanning the array and keeping track of how much dirt needs to be transported between consecutive bins. For example, EMD 0 equals 0. EMD I plus 1 equals I plus EMD I. By total distance equals EMD I. EMD-based similarity analysis. EMD-based similarity analysis, EMDSA, is an important and effective tool in many multimedia information retrieval and pattern recognition applications. However, the computational cost of EMD is supercubic to the number of the bins given and arbitrary d. Efficient and scalable EMD computation techniques for large-scale data have been investigated using MapReduce, as well as bulk synchronous parallel and resilient distributed dataset applications. An early application of the EMD in computer science was to compare two grayscale images that may differ due to dithering, blurring, or local deformations. In this case, the region is the image's domain, and the total amount of light, or ink, is the dirt to be rearranged. The EMD is widely used in content-based image retrieval to compute distances between the color histograms of two digital images. In this case, the region is the RGB color cube, and each image pixel is a parcel of dirt. The same technique can be used for any other quantitative pixel attribute, such as luminance, gradient, apparent motion in a video frame, etc. More generally, the EMD is used in pattern recognition to compare generic summaries or surrogates of data records, called signatures. A typical signature consists of list of pairs x1, m1, ... xn, Minnesota, where each she is a certain feature, e.g., color in an image, letter in a text, etc., and me is mass, how many times that feature occurs in the record. Alternatively, she may be the centroid of a data cluster, and me the number of entities in that cluster. To compare two such signatures with the EMD, one must define a distance between features, which is interpreted as the cost of turning a unit mass of one feature into a unit mass of the other. The EMD between two signatures is then the minimum cost of turning one of them into the other. History. The concept was first introduced by Gaspard Monge in 1781, and anchors the field of transportation theory. The use of the EMD as a distance measure for monochromatic images was described in 1989 by S. Peleg, M. Werman and H. Rom. The name Earth-mover's distance was proposed by J. Stolfi in 1994, and was used in print in 1998 by Y. Rubner, C. Tomasi and L. G. Gibbers. See code for the Earth-mover's distance. Python 2 wrapper for the C implementation of the Earth-mover's distance. C++ and MATLAB and Java wrappers code for the Earth-mover's distance, especially efficient for thresholded ground distances. Java implementation of a generic generator for evaluating large-scale Earth-movers distance-based similarity analysis.